Hello, ladies and gentlemen, herzlich willkommen, добро пожаловать, друзья. We begin with the third chapter of tutorial for calculation of rotating geometric parts. In this video I will show you how to run the calculation with rotating geometric parts using the pimpleFoam solver. This calculation will be based on rotating fan in room tutorial. If we take a look on pimpleFoam solver from the internet, we will find the following information. The pimpleFoam is a pressure-based solver designed for transient simulations of incompressible flow. It handles laminar and turbulent single-phase flows under isothermal conditions, accommodating both Newtonian and non-Newtonian fluids. Here you will see the further features which are responsible or which are in connection with this solver. Let me now observe the files which should be considered in order to run such simulation. For that I go to Run directory, and first of all, of course, the 0 folder. Here we will find K, nu, omega, pressure and velocity files. Let me open all of them. So in the K file we see its basic definitions in form file direction, basic definitions, the dimensions, internal field, and of course the boundary field. Here I have written how dimensions are listed and in which order they are listed. It begins with kilogram, then it goes forward to a meter, then the second, and the fourth one is the Kelvin, fifth one is mole, and then we have the ampere and candela. So the dimensions for K file are meter square per second square. Internal field is defined as 0.00341. Boundary field contains 2 times zone rotation, defined as cyclic army, and all other boundaries. You can easily copy these settings for all walls if needed. Let me close this. So in new file we will see also the form file definitions, also the dimensions, internal field, and of course the boundary field. So this is quite the same as it was in K file. Dimensions are meter square per second. You see also here the zone rotation and walls definitions in boundary field. So let me go forward to omega. Omega dimensions is per second, 1 per second. So internal field is uniform. We have also here the zone rotation defined as type cyclic army. And I close this. Here I see the pressure field defined as meter. Defined definitions are meter squared per second square. So internal field is uniform, 0 Pascal, and so walls blower, walls outside, walls rotations are defined as flux pressure. Zone rotation is defined as type cyclic army, and of course we come to the last one, the velocity file. This dimensions here are meter per second, as it usually defined in velocity. internal field is uniform 0, 0, 0 in all direction. Boundary field also includes zone rotation and all other walls. The walls below and outside are defined as no slip, and walls rotated are defined as moving wall velocity type. So let me close all of it. Now we are ready with the 0 folder, and let us switch to constant folder. So the constant folder contains DynamicMeshDict, gravity file, transport, and turbulent properties. In dynamic, let me open all of them and consider each of it. The DynamicMeshDict, in DynamicMeshDict we define the rotating parameters. First we need to define the center point of rotation. This is the origin one. The point was taken as 0, 0, 0. The rotating axis is along the y-axis, so the definition is taken as 0, 1, 0. For that, it will be better if I start the paraview and show you the directions. So for that I go to paraview. Now it's open. I will find it in media, RAID, blower 2, run blower 2. Walls rotation and walls blower for better understanding. Let me show you the 0, 0, 0 point. It is here in the middle of the rotating zone. The y direction is the rotating axis. So now we have to come to omega. Omega is needed to define the rotation. Here I will go to calculation file. Calculation file. The diameter of rotating zone is 3 meters. I wish the velocity at the end of the rotating zone was approximately 100 km/h. In this case we have to choose the omega 1852. So this is the definitions according to 100 km/h. I want take simply 20 radian per second. For that I have to define the number of turns in 191, so that we have the omega 20. It's correct. And now the velocity will be close to 108 km/h or 30 meters per second. So the omega of 20 will be defined in constant folder and DynamicMeshDict. The linear velocity of at the end of rotating zones is about 108 kilometer per hour or 30 meter per second. It is also okay. So now you have to notice one rule in definitions of DynamicMeshDict. If the thumb of your right hand is pointing in the direction of the selected rotating axis, then your other fingers are pointing in the direction of the rotation. The omega should be a positive number. Now I close these files. Let me go to gravity file. Gravity file is also simple. The gravity is shown in -z direction. By transport properties is new defined, and dimensions are meter quadrat square per second. The turbulence properties file include the Reynolds average simulation turbulence model and all definitions for it. Now I would like to immerse myself in the div of the system folder. I select four files: controldict, createPatchDict, FV schemes and FV solutions. Let me open them and beginning with createPatchDict. The createPatchDict is very important. It contains both zones, zone rotation 1 and zone rotation 2. The zone rotation 1 is master patch, and zone rotation 2 is the slave patch. So the next steps, we consider the FV schemes. It is structured as follows and has the definitions taken from rotating fan in room tutorial. So FV solution, take it as it is. Now we will come to controldict. The controldict contains the main parameters for calculation, like application type, pimpleFoam, start time, end time, right interval, and so on. These parameters should be selected to achieve the visible movement of the rotating. I speak now exactly about right interval. These parameters should be selected to achieve the visible movement of the rotating walls. For example, 0.1 turns of the complete rotation. For that you can use such calculation files. For example, I want to take the movement of 0.01 turns of the whole turn, and the delta t should be selected as this number below. Here I have defined the right interval as 0.001, and the delta t is taken from the experience because I already have run this simulation, this kind of simulation, and 0.0001 is the very good delta t time step. Max current number should be taken as 4, max delta t as 1. Now we are ready to start the simulation. For that, I go to Run folder and open the terminal. Of course, I need to activate the OpenFoam. In order to start the simulation, I have to run the following commands. The processor should be deleted because they contain no zero folder, and we have to decompose it again. So I have to run the remove processors option. Then we see the zero folder is already exist, so we have to run createPatchDict and then decompose, and after that we will run the pimpleFoam in 16 process cores. So let me execute this command. So create patch will be done. So let me wait on it. So remember, first we start the simulation with the wrong mean wall definition. The calculation should be aborted after several time steps. Let me show you the previous settings on DynamicMeshDict. So you see the mesh quality control, and these settings of mean wall is exactly the wrong one. So after the calculation stopped, we will remesh the file, the case, and start running pimpleFoam again. Now we have the decomposer part creation. Let me wait on it, and you see it begins with processors. Constant file is already included, constant folder. After the decomposition of constant folder, we will see the zero folder. Let me show you. Zero folder is also included in processor directory. So now the simulation runs pimpleFoam in parallel. So let me wait a little bit until the calculation stops with an error message. So now you see the simulation stops with this error message. So after time of 0.003 seconds, the calculation aborts. We have here the definition of the error message: process received signal floating point exception. It is exactly what I was saying about. primary job terminated normally, but one process returned non-zero exit code. Per user definition, the job has been aborted. So floating point exception means I think that we have non-physical results, maybe zero division per zero, or something like this. So in order to do the normal calculation, we have to change the mean wall settings. For that I go to DynamicMeshDict and activate the mean wall definitions, where we have the definition of mean wall divided to 50. I save the changes on DynamicMeshDict and run the following command. I delete everything what was created before, all folders with processors and so on. So the case is empty now. Then I have to type this command, 16 cores, and do first step we will do the block mesh and new snappy hex mesh. Then we do the check mesh, and after that we will have to create patch, decompose par again, and run the pimpleFoam. So that is exactly what this command means. We will execute it, and it starts with block mesh. Then we have decompose par without zero folder. Processors now are created. No zero folder, as I previously mentioned. Now we have the DynamicMeshDict, which is running. So after the mesh will be created, I show you how the calculation starts. So the DynamicMeshDict is ready. We have now here reconstruct par mesh, then check mesh. Check mesh runs now. We have close to 3 million cells in total. Now you see we have only 2 failed check mesh. We have error in failed states and concaved cells. Determinant is okay. Now create patch is running. We have the decompose par section again. Constant file is included. Now we see that the 0 folder is also included in processor directory. So pimpleFoam starts, and let us wait for a while until we can do some consideration or investigations of results. Please look, we are already farther than 0.003 seconds. At this time the previous simulation was aborted, but now the simulation runs well. The mean wall definition as the mean cell volume divided to 50 causes the simulation to work as it should. I finished the calculation because the computer is too noisy. So I had to re-record the videos from this one because the background noise made it impossible to edit the video files. Now we have to observe the results. For the results I have to select internal mesh, I press F5 to update. And now I have to create the section in the middle of the rotating zone. It will be y-axis, don't show the plane, invert. I switch to velocity and change the color map to turbo. Click apply and close. So you see. Now we can consider the results, and I want one question. What is practically to do in this case? I think it is important to animate the flow movement and consider the velocity field in the video file. For that I have to save the animation. I go to File and choose the option Save the animation. Then I have to select the format OGV. Then I have to define the proper storage location and give the video file the name. The storage location will be media, rate, lower 2 screenshots, and give the name. So in this case I overwrite the existing video file flow velocity. Overwrite, yes. Now I have to define the frame ratio. It will be 10 frames per second and save it in the screenshot folder. Saving of the video file has started, and after a while we can consider the results. Let us wait a little bit. The animation is ready, and we have to open the corresponding folder where the file is saved. Here is it, and now we can start this file. That's it. Of course, it is possible to convert the OGV extended file to MP4 format. For that, we have to visit the internet site and type the command ogv to MP4 converter. I will type it, ogv to MP4 converter. That's it. We will choose the first one. First, we select the video. It will be flow velocity. Then we convert it. And after conversion, we download it. I have to go to the download folder, cut the video from this folder and place it here to the screenshots folder where the first video in OGV format is saved. Now I will show you the video files of another calculation, blower 1. I go to screenshot folder. The simulation in this case took more than 8 seconds. This is the folder where the videos are saved. Let me start the first video. When the rotation of the rotating blower part starts, the movement of the air volume at the outlet of the blower also starts. Now the flow is in the middle of the room. After several seconds, you see the flow reached the end wall and the flow is directed along this wall in all directions. You see the flow reach the opposite side and the flow moves in all directions along it. The maximum speed is about 30 meters per second. Let me stop it. Now we can also look at the original speed case. This is this one. I open it in the VLC format with VLC player. This is the original speed. Finally, we can observe the inlet side of the blowers in the ISO representation. Here is it in this video. Here we can see how the flow moves from the inlet to the blades and then due to centrifugal force reaches the end of the blades and then flees into the fan outlet. What is also important for me is to consider the mass flow rate through the fan outlet. Of course, it is possible to calculate the exact mass flow rate of such blower. After a lot of trials, I found the solution for it. For more details, please contact me. My contact details are at the end of this video. I don't wanna start any further analysis in this video. For more analysis, please observe the OpenFoam videos in YouTube, like rotating mesh simulation project tutorial in pimpleFoam or other tutorials. At the end, we discuss the necessity of such calculations. First of all, it is important to know how to simulate rotating geometries. With the flow rate, you can calculate the efficiency of the fan and modify the fan if necessary. It will soon be possible to extend this simulation and connect the fan to a pipe system with many outlets. This allows you to calculate whether enough air is flowing through the individual outlets, and if necessary replace the fan and or adjust the outlets so that the same volume flow passes through the individual of it. Now we can make the summary. What we have learned in these 3 videos. First of all, we prepared the boundaries in Salome, defined the bounding box, selected the edge length according to the global cell size, and have done the definition of the refinement levels. We defined the snappyMeshDict and other dicts for the mesh using the preform template tool. Then we generated the block mesh and snappy mesh on the Linux computer. We also examined the surface feature extract dict file. It was important to understand what the included angle does. Then we observed the parameter tolerance in snappyMeshDict. We also looked at the mesh quality settings and above all touched on min wall. Finally, we examined all the files that were necessary for the calculation. DynamicMeshDict and createPatchDict were the 2 most important of them. So now I close the recording. In further videos we will work through exciting topics again. So I wish everyone much progress with the simulation in pimpleFoam. See you in the next videos. Bye bye.